So hello everybody, we are back to our class again. So what we are studying nowadays is description of plasma kinetics, the orbit theory. So in our previous class, what we are studying the E cross B drift in plasma. And in that actually we have seen that when there is an electric field and a magnetic field which are perpendicular to each other, like in this diagram you are seeing that electric field is in the direction of y and magnetic field is pointing towards u, so it is in the positive z direction. It is a right-handed coordinate system. So in that case, what we are seeing that an electron is orbiting, and depending on the electric field, it is moving in a direction which is perpendicular to both electric and magnetic field, as we are seeing over here. I have done this numerical exercise in computer. You also can do that. You can just use the governing equations that I have written yesterday, that nothing but the Lorentz force equation. You can write these equations and you can solve these. Then what you will get the trajectory like this actually. So what we are seeing when electric field is 0, you know that this is exactly the case what we studied in the first class on this plasma particle kinetics in orbit theory, that it just makes an orbit. Now what I have done actually, I have introduced a little bit of electric field, 0.1 volt per meter, and that is in the y direction, and you have seen that the orbit started drifting like this, but because the electric field is very small, the orbit is drifting very slowly here. The moment you increase 0.1 volt per meter to 10 volt, or say 1 volt per meter, which is 10 times increase, then you see that now you are clearly able to visit that the orbits are drifting in a direction which is perpendicular to both your magnetic field and electric field, and drift is in the x direction. Similarly, when we are increasing it another 3 volt per meter, you can see that this is the kind of orbit and the kind of drift that the particle, here it is electron, that executes. So the most interesting part was that this kind of drift motion is independent of charge and mass of the particle. So then the drift velocity is E cross B by B square. Okay. Of course, the orbit radius will very much depend on the mass. You know that R is equal to mv by bq. So that way it will depend on all those things. But the drift velocity, that is just E cross B by B square. It is not having any charge or mass value. So the drift velocity is same for both ions and electrons. So in this class, what we are interested that we are now creating a magnetic field which is having gradient. Now here I have drawn a Helmholtz coil kind of configuration where there is a central zone where the magnetic field is pretty uniform. I have plotted the magnetic field in the z direction intensity, and that you are seeing that here it is more or less uniform, but at the core of this coil it is peaking, and on either side actually it is peaking here and is peaking here. You see the coil is over here and another coil is over here, and the fields are peaking over here. This is because the magnetic field lines are very much concentrated over here, that is giving a very magnetic high field intensity, and the same is here, and here the fields are diluted, when field lines are diluted, and you are getting a lower magnetic field value, but which is more or less constant in this region. And there are many applications where you use this for constant magnetic field kind of configuration where it is required. Now we will be using this configuration. This is mainly because you see that magnetic field is very high here, and then it is falling, and then it is starting a constant region, again it is increasing, and now this hilly region where the slope is there, you can see that we are able to maintain a slope which is more or less constant. You see that magnetic field is here maximum, it is falling, reaching a plateau region which is more or less constant there, and then what it does, it starts increasing with almost a constant gradient. So gradients directions are different here and here, they are opposite, but the magnitude is more or less same. That's what we have put over here. So whenever any charge particle which is basically confined in this region, they try to move this side or this side, they face a magnetic hill where the gradient is more or less constant. So when the particles are at a constant magnetic field, we know that the kind of motion which are there, it just starts orbiting around the magnetic field. But what happens when they try to reach a gradient which is more or less constant over here and here? The students where they find a little bit difficulty that how the magnetic field gradient is constant. So you can see here the fields are like this, when the field gradient is like this. I have plotted the magnitude of Bz and the del Bz by del Z, that is more or less constant. So we will be using this property that magnetic field gradient is constant, and what is the particle kinetics that may be possible in these regions. Okay, so we start that. Now you know that Maxwell's equations, which always comes to rescue us in every situation wherever we find problem. So, and it is valid in all situation. So it is divergence b equal to 0, and what we get actually if we write it in cylindrical coordinate, this is the kind of thing. And theta symmetry we are assuming, so we are not putting it over there. Now here what we are seeing that this del Bz by del Z part which is over here, we want to assume this as constant for this particular case. Now you see that again we have plotted the this right-handed coordinate system, and a particle is orbiting like this. And what happened actually, this magnetic field lines, magnetic field Bz is like this. So it is having, B is having two components, one is Bz and one is Br. This Br is having a radial component, this is the radial component, and Bz is the axial component. Okay. So now we know what is Br and what is Bz, and what we are assuming that this del Bz by del Z, this part is constant over here. Okay. Now what we are seeing over here, that if del Bz by del Z is constant, then we can write this equation in this form, and you can convert it in this form. Then you can see what is there inside the bracket. Here it is RBR, and here it is R square by 2 del Bz by del Z, and there is the equal sign, there is an equal sign, and what is there, that both are derivatives. So we can compare these two, and we can get that BR is R by 2 del Bz by del Z, because this R cancels, and then you are left with R by 2 del Bz by del Z. So if we are having an orbit of radius equal to capital R, then what you can see that BR equal minus R by 2 del Z by del Z. So this is coming under the condition when del Bz by del Z is constant. And how you can make a configuration where del Bz by del Z will be constant, that we have seen just in our previous case, that this is the configuration where we have put this. You see that is just del Bz by del Z in this linear part, that is more or less constant, and we are using that property, and we are using Maxwell's equations to get a relationship between Br and del Bz by del Z. Okay, so what we now find that the relationship is Br equal to minus R by 2 del Bz by del Z. So we remember this, and we will be using this in the next conclusions, whatever we arrive there. So now we start with the equation of motion. All these equations of motion are very much known to us. Nothing is new here. We have studied all these in our school days or maybe higher secondary classes. Now you see that the first one. What is that? This is mv perpendicular square by r equal to qv perpendicular into bz. And you know our nomenclature that whatever in the axial direction either we put as z or we put as parallel, whereas whatever the orbital motion, that orbital velocity we put as b perpendicular, which is perpendicular to the magnetic field direction, and that is what. So this is the orbital centripetal force mb perpendicular square by r for that orbit of radius r, and q v perpendicular cross b, this is just the Lorentz force. So these two are balancing, and then what we are getting, that whatever the orbit, that will be getting from here. So we just, for the timing, we keep it like this. And then if we write the equation of motion, you know that this is the axial force balance. So this is m dv dt bz dvz, so it is in the axial direction, and we have put qv perpendicular br. So we go back to that this thing. See, this is your v perpendicular, okay, and this is your br. So br in the plane of the board and v perpendicular also in the plane of the board, and so if that is there, then v perpendicular cross br, there the angle is 90 degrees, so that will point in a direction of the z. So that is why this is contributing in the axial direction of motion. Similarly, if you put the other one, what we have put over here, see v perpendicular cross bz. So if you go back here, this v perpendicular and this is bz, so this will be in the radial direction, this cross product. So that is why it is contributing in the this centripetal force equation. So this is balance is because of that, and this is the axial motion. Now what we come, this q v perpendicular br, we have got one relation for br just a little before. So here it is br. You see br is equal to at r equal to minus r by 2 del vz by del z. So what we do, we just put that thing over here. So this br we have put over here. So this is r by 2 and del vz by del z. We have just a little bit rearranged, and this is coming like this. Now what we do it again, that we write q v perpendicular by 2 pi r. So we have introduced one pi at the bottom. So we introduce a pi at the numerator also. Here this pi, so these 2 pi are cancelling. So this pi you have put over here, and because we have put a r at the denominator, so we are putting one r in the numerator. So this r and this existing are multiplying and becoming square, and pi is already there. So now you see that, what is that? Q v perpendicular by 2 pi r. So apart from q, v perpendicular by 2 pi r, that gives you the orbital frequency. So q into frequency, that gives you the current, and then current into pi r square is the cross section of the orbit. So area. So current into area gives you the magnetic moment, and then this del z is there. So what we are getting from this axial component of motion, that q dvz by dt equal to minus m of del vz by del z. So that is there. So this equation we note it over here, that dv dz equal to minus m by m, small m. M is the magnetic moment, and this del vz by del z. So we have put in a red square box, so that we highlight it, and we will be using it in a later derivation. Now you know that total kinetic energy is a constant of motion, because you are not putting any external applied force. So this total kinetic energy is having two components. One is kz, so that is the kinetic energy because of motion in a direction parallel to the magnetic field which is applied in the z direction, and k perpendicular which is the orbital kinetic energy. So that is nothing but half mv perpendicular square. So k perpendicular equal to half of mv perpendicular square, that is equal to half of, now you see that what we have put over here. So v perpendicular square, this one, you see that mv perpendicular is equal to qr v perpendicular into bz, right? So we just take this mv perpendicular square value from here and we put it over here. So then what we get, half is there and then q v perpendicular bz into r. So that is just what is coming over here. Now you know that what is that value actually. Now this one is q r v perpendicular into bz, and here you see that q r v perpendicular is there, and what we got from there apart from del bz del z, you see that half of q r v perpendicular, that resulted in m. So we just get our m over here, the same thing, so m bz. So what we are getting, k perpendicular is equal to m bz. Actually this derivation we made earlier also. If you remember, we can go back and we can show you that we have written that. You see that here m equal to k perpendicular by bz. So the same thing, magnetic moment is always follows the relation. So this is k perpendicular by bz, and we have arrived here the same thing over here as well. So this is k perpendicular bz is equal to m. So that is lying over here. Now we take a derivative of this kinetic energy due to axial motion, that ddt of half m vz square. So you know that this is the axial kinetic energy and this is kz. So I can write this as k minus k perpendicular. So exactly that what I have done here. So it is d dt of k minus k perpendicular. Okay, this one kz. So this is half m bz square, and that is k minus k perpendicular. Okay, so I write it like this. Now what happens in the total kinetic energy constant of motion? So what I can do, I can take this derivative as 0. So what I am left with is minus d dt of k perpendicular. And you know that k perpendicular is what? This is m bz. So I put that m bz over here. So we get d dt of half of m bz square equal to minus of d dt of m bz. So m bz is within the bracket and d dt is outside. Now again we know that d dt of half m bz square, using standard derivation formula, we can write it as m bz dbz by dt. That is always true. So this vz is nothing but dz by dt, and the same is over here, and then lying here dvz by dt. So what we are now getting, that dz dt is over here and dvz dt, that value we have already derived over here. You see that there m dvz by dt, that equal to minus of m del vz by del z. So we take this value, this was highlighted over here, dvz dt equal minus m by m del vz by del z. So we just put that over here, and then what we are getting, m dvz we have put minus m into dvz by dz, and because it is outside, so I am taking m out, and dz dt and dvz dz, that is finally resulting in d dt of bz, where bz is inside. Now you see that what we have done, we have taken the derivative, time derivative of the same quantity. What is that? That is axial kinetic energy, half m bz square. One has resulted in minus d dt of m bz, where m bz is within the bracket inside the argument, and then here what we are getting, we are taking the same derivative of half m bz square, and we are getting minus m of dvz by dt. So what it essentially means? It essentially means that minus d dt of m bz equal to minus m of d dt of bz. For this kind of configuration, you remember, where del bz by del z is constant. That was the condition that we have started with. So in such configuration, we are seeing that ddt of mbz is same as m of ddt of bz. So when does it happen? This is possible only when m is constant. So for this kind of configuration, magnetic field configuration, where gradient of Bz is constant, we are seeing that magnetic moment is a constant of motion. So this is a very important conclusion, and it has immense technological consequences which we will learn a little later. So what we see here, that m equal to k perpendicular by bz is equal to half mv perpendicular square by bz is a constant of motion when the gradient in magnetic field is constant, del bz by del z is constant. So what essentially we are getting for this kind of dynamics, so let us analyze over here. So I have chosen some 1, 2, 3, 4 and this 5 quantities, and we'll analyze these 5 quantities and we'll try to understand what is the kind of dynamics. So what do we see on the first one? Magnetic flux. You know, this flux is nothing but the quantity you multiply by the perpendicular cross section. So this is bz into pi r square, and then what we are getting here, we are taking this pi out, bz over here, just mathematical rearranging of terms, and this r. For orbital motion, if the velocity is v perpendicular, this orbital velocity, we know that the radius of gyration is equal to m v perpendicular by bz into q. So exactly we are just putting that value over here and making a square. So everything is getting a power of 2. So m square v perpendicular square divided by q square bz square, because mv by qb is the radius and you are putting a square of that. So it is coming like this. And then we are a little bit rearranging the terms in a bit meaningful manner. So what is here? We have multiplied by 2 over here, and then pi is lying here, and we have introduced 1m over here. So m square, 1m is coming over here. So mv perpendicular square is going there. Because we have introduced a 2, so half mv perpendicular square is remaining over here. So what is that? Half mv perpendicular square? That is nothing but the kinetic energy due to perpendicular orbital motion, that perpendicular to the direction of the magnetic field. So that is k perpendicular, as we have defined already. And you know, this bz, one bz is cancelling with another bz, and you are just left with one bz here. So this bz is lying over here, and q square, as usual, we have kept it over here. So what we are now left with, it is 2 pi m by q square and then k perpendicular by bz. Now you just notice very carefully, you know that m is constant, q is constant for a particular charge, and then just we have learned that k perpendicular by bz is nothing but the magnetic moment. So the whole quantity 2 pi m by q square into m, that is constant of motion. So a very interesting thing we have now arrived, that for this kind of motion, when there is a gradient in magnetic field and that gradient is constant, the magnetic flux is a constant of motion. Very interesting thing, and we will use this property in our later derivation, and we will see very interesting consequences. So here what we are seeing, you see that orbital velocity. So this is v perpendicular, you know that it is qb z r by m. So it is a very standard, and you have derived it so many times, that it is qb z r by m. Now what we are doing, q is here, bz is here, then we are putting one r over here, and then we are putting m here, and m was already there, and another r here, so to balance that thing. Now what we are getting here, q by mr into bz into r square. Now you see here Bz into r square, what is that thing? That is the magnetic related to magnetic flux, and you can write it in terms of magnetic moment. So I have written like that, and it is coming to be as 2m by r cube. Now here you see m is constant, q is constant, so I can say that v perpendicular is inversely proportional to 1 by r. So what we are saying here, that orbital velocity is inversely proportional to the radius of gyration. So tighter the gyration, faster is the orbital motion. Okay, and larger the orbit, slower is the orbital motion. So this is very interesting. So as it goes to tighter and tighter orbit, it makes faster and faster gyration. So this is the consequence from here. Again, you remember that this is the case when you have a constant gradient of magnetic field. Then the axial velocity. This is very interesting. You see that Vz is equal to, I have just written, this is the total kinetic energy, this is the perpendicular motion kinetic energy, and this one is half mvz square. If you just remove the square root, it will be coming like that. So essentially we have used the equation that total kinetic energy is sum of the axial kinetic energy due to axial motion and kinetic energy due to orbital motion. So I have just taken that, redistributed the term, and we have extracted out the axial velocity component Vz. So what is coming? It is coming as Vz is equal to 2 by m square root of k minus half of m v perpendicular square. So if that is the case, then what you can see, the more the orbital motion, less is the axial velocity. So if a particle gyrates faster and faster, it will move slower and slower. So this part is very interesting, because we will see that if the orbital motion is so fast that can make the axial motion almost equal to 0, then that is a case when the particles stop moving in the axial direction, and that is something related to confinement. So if you are making a device and you are not willing to make the particle move away from certain zone, then if you are able to make Pz equal to 0 at that zone, then the particle will not cause that region. So that is what is very much important implication of that, and we will go into some details of that in some later slides. And let us go to the next one, that is the acceleration. You see that we have derived this relation. What is that? dvz gt is equal to minus m by m del vz by del z. Okay, so where we have seen that? So this is one, dvz by z is equal to minus m by m del vz by del z. So this is actually something what is very interesting over here, that this is a minus m by m del vz by del z. So what we are seeing here, that higher the gradient, this is a deceleration basically. So higher the gradient, more is the deceleration. So the particle will not be moving in that, whatever the energy, that will be getting decelerated, and it may happen that at one point it will stop. And what we see that k perpendicular is proportional to bz, because m is constant. So the orbital motion is more when the bz is more. So we stop here in this class, and we will come back in the next class, and we will deal more with this. Okay, thank you.